Good morning. So, today we will continue with our discussion on hyperbox classification. So, in the last class what we have said is if the feature samples, the feature vectors belonging to different classes, they are mixed in an arbitrary manner, then we cannot really design a linear classifier or a quadratic classifier to classify the different samples to different classes. So, in such kind of situation, the kind of classifier that we have talked about is hyperbox classifier, where you divide the feature space into a number of hyperboxes and the different hyperboxes will be given different class levels. And then when an unknown sample comes, then if the unknown sample falls in one of the hyperbox, is well within a hyperbox which is which belongs to a particular class, then this unknown sample will also be classified as belonging to the same class, which class level, the class level that has been given to that particular hyperbox. Whereas, if the unknown sample falls outside the hyperboxes, outside any of the hyperbox, then you find out what is the distance of this unknown sample from the hyperboxes, and based on the distance we can give a fuzzy membership grade, and to whichever class the fuzzy membership function is maximum, we can classify the unknown sample to that particular class. Okay. And for that we have said yesterday that a fuzzy membership function or a trapezoidal fuzzy membership function that can be employed, which is like this. So, if this is the direction of the feature and on this side I put the membership value, which is mu, and the fuzzy membership function, if I define something like this, a trapezoidal fuzzy membership function, where these are the mean points and max points, because as we said that the hyperbox can be represented by a mean point and a max point, and accordingly it is called a mean max hyperbox. Okay. So, if I have a fuzzy membership function, a trapezoidal fuzzy membership function, something like this, and we have given an analytical expression for this sort of fuzzy membership function, which is given by so we can define, we can give an analytical expression of the fuzzy membership function something like this, where A is the input sample vector, Vi represents the mean point in the ith dimension, Wi represents the mean point, the max point in the ith dimension, okay, and gamma is a parameter which represents the degree of fuzziness. So, as we said that if the value of, because the slope of these lines, they depend upon the value of gamma. Okay. So, if the value of gamma is more, then the fuzziness will be less, it will be more towards hard classification, because if I increase the value of gamma, I will have these slanting straight lines something like this, whereas if I reduce the value of gamma, then I will have the straight line something like this, which increases the fuzziness. So, this gamma actually controls the degree of fuzziness. Okay. So, you can compute, given a min max hyperbox where I know the mean point V and the mean point W, and this is what I have given only the membership calculation, the membership computation only along the ith dimension. So, such membership computation has to be done among all the n dimensions added together, and then you normalize with respect to n. Okay. So, once I have this sort of analytical expression for computation of the membership function. I can compute the membership of an unknown sample to different hyperboxes, or because in this case I will have for every class a number of hyperboxes. So, considering a particular class, say class C 1, which have say m number of hyperboxes. Okay. So, a class C 1 may have m number of hyperboxes. Okay. So, accordingly, for each of this hyperbox, I will have a membership function of this form. Okay. So, there will be mu I for class C, let us, if I put it like this. So, mu I C, okay, for I varying from 1 to m, as I have m number of hyperboxes. So, for each of these hyperbox I will get a membership function. Okay. So, I will have m number of membership functions like this, and the maximum of this, maximum over I, okay, this gives me what is the membership function of the hyperbox belonging to class C 1, which is nearest to this unknown sample. Okay. Because obviously, a hyperbox which is nearest to the unknown sample, that hyperbox will give the maximum membership value, and the hyperbox which is furthest from the unknown sample, that hyperbox will give the minimum membership value. Okay. So, I take the maximum of these m number of membership values given by m number of hyperboxes belonging to class C, and this maximum value is the membership value of this unknown sample to class C 1. Okay. So, what I have to do is I have to compute the membership function with all the hyperboxes. Then for a particular class, I have to take the maximum of the membership functions, and that give the membership value to that particular class. So, that way I get the membership values to all other classes, and now whichever class gives the maximum membership value, I take or I classify this unknown sample x to that particular class. Okay. So, this is how this hyperbox classifier has to work. Now, in the year 1992, Patrick Simpson, he said that this concept can be converted in the form of a neural network. Okay. So, accordingly, a neural network architecture, which is fuzzy min max neural network. Okay. So, FMNN or fuzzy min max neural network for pattern classification was proposed by Patrick Simpson in the year 1992. Okay. So, what is this concept of fuzzy min max neural network? The fuzzy min max neural network, it has got one input layer, one output layer, and one so called hidden layer. Okay. Now, this output layer is same as the number of classes that we have. Okay. So, this is equal to the number of nodes in the output layer is same as the number of classes. So, if I have C number of classes, there are C number of nodes in the output layer. Okay. Similarly, number of nodes in the input layer is same as before, that is equal to the dimensionality of the feature vectors. Okay. So, this number of nodes in the input layer will be D, which is nothing but dimensionality of features or feature vectors. Okay. And the hidden layer nodes, they actually represent hyperboxes. Okay. So, it is the responsibility of the hidden layer nodes to compute this membership function. Okay. So, if the hidden layer nodes has to compute this membership function, then the hidden layer nodes or every hyperbox, as I am saying that these hidden layer nodes, they represent the hyperboxes, they have to know what is the corresponding min point and max point. Okay. So, the min point and max point is represented in the form of connections. Okay. So, the connection between the input layer nodes and the hidden layer nodes will be represented by two matrices corresponding to the min point V and the max point W. Okay. So, I will have all these connections from input layers to the middle hidden layers, something like this, where these connections actually represent the min points and the max points. Okay. And these connection weights are represented in the form of two matrices, one matrix corresponding to the min point and one matrix corresponding to the max point. Okay. And the connection from the hidden layer nodes to the output layer nodes, as I said that these output layer nodes represent different classes. Okay. So, if an hyperbox say B j is given the class level of class C I, then only I will have a connection from this hyperbox B j to the corresponding output node C I. Okay. And for a hyperbox which does not belong to a class, a particular class, there will be no connection from that hyperbox to the corresponding class. Okay. So, I can represent this connection weight from the hidden layer nodes to the output layer nodes by another matrix say U, okay, where the elements of the matrix U can be either 0 or 1. If it is 0, say U I j, if an element U I j is equal to 0, that represents that I do not have a connection from the ith node in the hidden layer to the jth node in the output layer. That means, the corresponding hyperbox, ith hyperbox does not belong to that class C j. Okay. Whereas, if say U P q that is equal to 1, that indicates the hyperbox pth hyperbox in the hidden layer belongs to the qth class, okay, and the corresponding element in the matrix U will be set to 1. Okay. So, accordingly, I will have connections from the hidden layer nodes to the nodes in the output layer. So, this being binary, either I will have a connection or I will have no connection. So, these connection weights are either zeros or ones. Okay. So, as before, you feed the input vector to the input layer node. Okay. So, these input vectors are passed on to the hidden layer nodes. The hidden layer nodes know what is the min point and max point of the corresponding hyperbox through these matrix elements U and V and W. Okay. They compute the corresponding membership function, right. So, the architecture of a node in the hidden layer will be something like this. It will have the connections corresponding to U and V, or the inputs U and V and W, which are the min points and the max points. It will also have the input vector A, unknown vector A, right, and it will give me an output which is nothing but this function B A V J W J. So, if this node, this is the jth hyperbox nodes, let us represent it by B j. Okay. So, in this architecture, each of these hidden layer nodes will compute the corresponding membership function, right. So, when B j, say jth node, because all these hyperboxes are to be created during the training operation or learning operation. So, if this B j is connected to say a output class C I, so I will have this corresponding connection weight to be equal to 1, right. So, this output membership value is collected by this output layer node C I. Okay. Similarly, if I have another node, say B 1, that might also be labeled as class C I. So, this hyperbox B 1, it will also calculate the corresponding membership function, okay, and that membership value will be passed on to this node C I. So, this node C I actually gets the membership values from different nodes, which are computing the membership values in the hidden layers. Okay. And finally, the responsibility of this node C I will be to make a fuzzy union of all these membership values that it gets. Okay. And this fuzzy union is nothing but a max operation. So, it finds out what is the maximum of the membership values, okay, and that maximum is taken as the membership value of this unknown vector to this class C I. So, that way each of these output layer nodes will compute the corresponding membership value. Okay. And as we said earlier, that outputs of these output layer nodes or the membership values computed by these output layer nodes, that itself can be taken as fuzzy classification, or if I want to form a hard classification, I will take the maximum of these values, okay, and whichever output node gives me the maximum membership value, I classify the unknown sample to that corresponding class. Okay. So, how the training process or the learning process will continue? Suppose I have got m number of samples, okay, training samples. The training samples are labeled as belonging to different classes. I take the samples one by one. Okay. So, whenever a sample is taken for the first time, I have to create one hyperbox node. That means, I have to create one node in the middle layer. Okay. So, initially what I have is, I have these output layer nodes, I have these input layer nodes. Number of output layer nodes is fixed, that is same as the number of classes that I consider. Number of input layer nodes, that is also fixed, it is same as the dimensionality of the feature vectors. The nodes in the middle layer or the hyperbox nodes, they are created while training. Okay.
Sir, since every hidden layer node is connected to input layer node, so it's getting A, but how it's getting Vj and Wj?
That is in the form of connection weights. That is given in the form of connection weights. Okay. And over here, unlike in other neural networks like perceptron, single layer perceptron or multi-layer perceptron, where we make unweighted summation of the input feature components, that is a linear equation. Here it is not a linear equation. Here each of these nodes have to compute this membership function, this membership value. Okay. So, whether you call it as weights, connection weights, or some information available to the input layer node, to the hidden layer nodes. The information, as I am saying, is represented in the form of two matrices V and W, okay, where matrix V will give you the min point information, matrix W will give you the max point information. Is that okay? So, a particular element Vij, okay, represents what is the min point. So, if I consider that this is the information going from the ith node in the input layer to the jth node in the middle layer, if I consider this. Okay.
So, here basically two weights are associated with each.
Two weights are associated with every node, one corresponding to the min point, one corresponding to max point. Okay. So, these hidden layer nodes, they only know need to know this information, min point, max point, along with the feature vector which is to be classified. Is that okay? Yeah. So, while training, as we are giving a number of labeled samples for which the class belongingness is already known, and initially what I have is, I have these output layer nodes, I have these input layer nodes, okay. I have 3 empty matrices, right, one corresponding to U, one corresponding to V, one corresponding to W. These matrices are empty initially, okay. And this hidden layer, that is also empty, there is no node in the hidden layer. Okay. So, while training, I take the first training sample, okay, and because this is the first training sample that I am encountering. So, as we have said in case of Hyperbox creation, that I have to create one node in the hidden layer, right, and corresponding to that I have to fill up this V matrix and W matrix, right. What will be the V and W matrix? Initially V and W will be identical, because I have only one hyperbox, only corresponding to a single point. So, min point and max point will be same, right. And I also have to establish the connection from this created hyperbox to this one of the hyperboxes in the output layer, one of the nodes in the output layer. Okay. So, what I will do is, if the first point that has been taken that belongs to class C1, okay, I will make the corresponding entry in the U matrix to be equal to 1. All other elements in the U matrix are 0. That means, I am making a connection from the hyperbox which is created in the middle layer to the class node C1 in the output layer. Is that okay? Whereas, other connections from hidden layer to the output layer, they are missing. All of them are represented by 0 in matrix U. Is that okay? Next time I get the second point. Second point either may belong to same class C1 or it may belong to another class. If it belongs to another class, then what I have to do is, I have to create another node in the middle layer corresponding to another hyperbox, and that will also be a point hyperbox, because I have not encountered any point belonging to that class earlier. Okay. So, that will be a point hyperbox, and accordingly I have to enter the information in V matrix, W matrix and U matrix. Okay. I get the third point, assuming that for this class of the third point, I already have created one hyperbox in the middle layer. If I assume that one or more hyperboxes in the middle layer, then I have to try to see that whether this third point, for which at least one hyperbox has already been created, whether this third point can be accommodated in one of those hyperboxes or not. Okay. If it falls within the hyperbox which is already created, I do not have any problem, I do not have to create any new node for that. But if it is outside the hyperbox, and for that class one or more of the hyperboxes has already been created, then the first what I have to check is whether this new point can be included in one of the hyperboxes, or I have to create a new node for this new point. Okay. So, the way this new point can be included in one of the hyperboxes is that you would select a hyperbox which is nearest to that point, okay, and expand the hyperbox, whether if the expansion is permitted. So, I have to have a criteria to decide whether the expansion is permitted or expansion is not permitted, because as we said that when we try to stitch a hyperbox, then there is a risk that samples belonging to other classes will also be included in the same hyperbox. Okay. So, accordingly I have to put some constant whether or how much a hyperbox can be expanded. Is that okay? So, this expansion criteria for hyperboxes is given by this: in theta which is greater than or equal to summation maximum of W j I A I minus minimum of Vji ai, okay, I varying from 1 to n when I have n number of dimensions. Okay. Whereas before Wji represents the ith dimension of the max point of jth hyperbox. Okay. Similarly, this is the ith dimension of the min point of the jth hyperbox. Okay. Ai is the ith component of the feature vector which is to be included in the jth hyperbox. Okay. So, if I expand a hyperbox, then naturally its min point and max points, they are going to be disturbed, right. And as we said that the max point is nothing but the maximum coordinate value of all the feature vectors within that hyperbox. Okay. So, the new max point in the ith dimension will be maximum of these two, okay, assuming that this max point will be going to shift to ai. So, maximum of these two will represent the new max point and minimum of these two will represent the new min point. And the difference between the min point and max point, that is going to tell you what is the spread or width along the ith dimension. Okay. So, sum of all these widths in different dimensions in all the n dimensions, that must be less than n into theta. As long as this condition is satisfied, we are allowed to stretch or expand the hyperbox. The moment I find that this value exceeds n into theta, then expansion of the hyperbox is no more permitted. Okay. Where this term theta is called the expansion parameter. Is that okay? So, while trying to incorporate a feature vector in a class for which some hyperboxes has already been created, I have to first try to see whether the hyperbox can be expanded to include this feature. If the expansion is permitted, then I will simply expand the hyperbox. And over here expansion of the hyperbox means I have to modify the min point and the max point. So, I do not have to create any new hyperbox. What I have to do is I have to change the min point and max point of an existing hyperbox. That means, I have to change the values in the V matrix and W matrix. That is the only thing I have to do. I do not have to do anything else. If I have to create a new hyperbox, then I have to make a corresponding entry in the V matrix, W matrix. I also have to make an entry in the U matrix. But in this case, U matrix entry already exists, because one of the existing hyperbox I am going to expand, only the min points and max points are to be modified. So, that modification I will do in the V matrix and W matrix. Okay. So, that is how the learning will continue. But while doing learning, as there is a provision of expansion of the hyperboxes, other problems may come in. That is, it is possible that a hyperbox I am expanding that overlaps with another hyperbox. Okay. So, let us just take an example to see that how this overlapping or expansion may affect our performance of the fuzzy min max neural network. So, let us take few points belonging to say two different classes, class 1 and class 2. So, I take a point A whose coordinates are say 0.7, 0.7, and suppose this point A belongs to class 1. I take a point B whose coordinates are say 0.75, 0.75. Suppose this also belongs to class 1. So, these are the points of feature vectors, two dimensional feature vectors, for which these are the class belongingness that is specified. Okay. So, let us assume that these are the training vectors using which I have to generate the hyperboxes. Okay. So, let us take these points one by one. So, I take this two dimensional feature space. So, let me consider this two dimensional feature space. Okay. So, you find that the first point that I have, that is A, whose coordinates are 0.7, 0.7, and this sample belongs to class 1. Okay. So, I take 0.7 over here. So, this is 0.7, 0.7, okay, and this sample belongs to class 1. The next point is 0.75, 0.75, that also belongs to class 1. Okay. So, this 0.75, 0.75 will be somewhere here, and this point belongs to class 1. So, initially I will have one hyperbox where the min point max point will be same as 0.7, 0.7. Okay. Next time another sample belonging to the same class having values 0.75, 0.75 comes, and because it belongs to the same class. So, I have to try to see that whether this hyperbox can be expanded to include this particular point, right. Now, assuming that depending upon the value of theta, this hyperbox expansion is permitted. Okay. So, I will have a new hyperbox which is given by this. Okay. So, this will be an hyperbox corresponding to class 1. Next, I have a point given by 0.9, 0.9 which belongs to class 2. Okay. So, I have this point, this one 0.9, 0.9 which belongs to class 2, a point over here. Okay. The next one is 0.8, 0.8, that also belongs to class 2, this one. So, 0.8, 0.8 that belongs to class 2. So, initially I will have one hyperbox for this. Okay. Next, I have to see that whether for this one, this hyperbox can be expanded to include this point, and let us assume that this expansion is also permitted. Okay. So, I will have this hyperbox corresponding to class 2. Okay. Then I will have this point for class 1, that is 0.1, 0.1, 0.1, 0.1 is somewhere over here, this belongs to class 1. Then I have this 0.2, 0.2, that also. So, when I have this, you find that I have already an existing hyperbox, this one, which also belongs to class 1. So, if I try to include this by expanding this hyperbox, you find that the hyperbox size will be quite big. Okay. So, here this expansion may not be permitted by our expansion criteria. So, if this expansion is not permitted, then I have to create a new hyperbox for this point. Okay. So, assuming that this new hyperbox has been created. So, the next point that I take is 0.2, 0.2 which also belongs to the same class 1. So, I have 0.2, 0.2 over somewhere over here. So, now I have one hyperbox corresponding to class 1, I have another hyperbox corresponding to class 1. Okay. So, I have to try to see that which one can be expanded to accommodate this. Okay. So, here you find that this is the nearest hyperbox and assuming that this expansion is permitted, I get a hyperbox of this one. Okay. Then I have to take the other training samples. So, I have this 0.3, 0.3 which belongs to class 2. So, 0.3 somewhere over here which belongs to class 2, and I have 0.15 which also belongs to class 2. So, 0.15 is somewhere over here. Okay. So, when I have created this hyperbox for class 2 was already existing, but again supposing that this expansion is not permitted, this was not expanded. So, I had to create a new hyperbox. Here I have to create another hyperbox if this expansion is not permitted. But now, let us assume that this expansion is permitted. So, I have the new hyperbox which is something like this. Okay. So, here you find that what I have is an overlap, because this hyperbox belongs to class 1, whereas this hyperbox belongs to class 2, and these two hyperboxes overlapped. Okay. So, we will see that how to tackle such overlapped situation. Let us take other training samples. So, again I have this point 0.45. So, 0.45 is somewhere over here which belongs to class 1. Then I have 0.5 that is somewhere here, that also belongs to class 1. Okay. And suppose these two form one hyperbox. Okay. And next I have this 0.42, which is, this was 0.45. Okay. So, 0.42 will be somewhere over here, right, and then I have 0.55 which is somewhere over here, and assuming that these two form a single hyperbox. So, I have a situation like this. So, here you find that one hyperbox belonging to class 1 that is completely enclosed within another hyperbox belonging to class 2. So, as the expansion of the hyperboxes are permitted, such types of overlap is likely to occur. So, the question is how to tackle such overlaps. Okay. So, this is actually what is called an overlap, and this is what is called containment, because one hyperbox belonging to one class is fully contained in a hyperbox belonging to another class. Okay. If I expand this definition, that it may not be necessary that the hyperbox is completely contained within another hyperbox. It is also called containment if at least one dimension of one hyperbox is completely contained within similar dimension, the same dimension of another hyperbox. Okay. So, here you find that if I have this overlap or containment within hyperboxes belonging to the same class, I do not have any problem. That is permitted, because the hyperboxes belong to the same class. But if the hyperboxes belonging to different classes, either there is containment or there is an overlap, then I have a problem in computing the membership function in this overlap region. Over this region, I cannot compute the membership function, okay, because over this region, if a sample falls, I will get the membership function of 1 for class 1, I will also get membership function for 1 for class 2. Okay. So, over this entire region, the classification cannot be performed. Similarly, over here, if a sample falls within this, to which class we should say whether the sample falls in belongs to class C1 or the sample belongs to class C2. Okay. So, I have similar kind of problem if such types of overlap or containment occurs while training this fuzzy min-max neural network. So, I have to have ways of dealing with this sort of problem. So, what we have seen so far is that I can have either an overlap of this form, That is, I have an hyperbox of one class, I have an hyperbox of another class, and these two hyperboxes overlap. Okay. Or I can have a situation something like this. I have a hyperbox of one class which is fully contained within the hyperbox of another class. This sort of situation. Okay. So, when this sort of situation occurs, then Simpson said that you go for contraction of the hyperbox, because if hyperboxes belonging to different classes, they overlap or one contains another, such a kind of containment or overlapping cannot be permitted. So, you go for contraction of the hyperboxes. Okay. And when you go for contraction, you have to contract along the dimension of minimum overlap, so that the disturbance incorporated in the hyperboxes which are already created, that is minimum. Okay. So, when you contract this, then what I have to do is I have to break it somewhere in the middle, over here, assuming that this is the dimension of minimum overlap. Okay. So, I get new hyperboxes. One hyperbox will be this, and the other hyperbox will be this. So, this is one hyperbox after contraction, and this is another hyperbox after contraction. And for contraction, what I have to do is I have to simply modify the min point, max point, nothing else. Okay. So, by this contraction, you find that the overlap between the two hyperboxes belonging to two different classes, that has been removed. But at the same time, I am incorporating some amount of error at the time of training itself, because this region for which information was already gathered, one is this region and another is this region. For these two regions, information was already gathered. Okay. So, by this contraction process, that information has been lost. And not only that, when I have created this min max hyperbox, this was the min point of this hyperbox and this was the max point of this hyperbox. By this contraction, you find that the this min point of class 1 has been put into class 2, right.
Sir, here contraction is done along first feature.
I am not saying first feature, it is along the feature along which the overlap is minimum. It may be first feature, it may be second feature, it may be third feature, it may be any feature. It is along the feature dimension along which the overlap is minimum. Okay. So, you find that this min point of class 1, that has been put into the hyperbox of the second class, and the max point of class 2, that has been put into the hyperbox of the first class. Okay. So, while training itself, I am introducing some amount of error. So, if I introduce some amount of error while training, so it is quite natural that while testing or when I get unknown samples, the performance will be poor, because I cannot maintain the accuracy during training process itself. Okay. Similarly, over here also I have to go for contraction. So, after contraction, the hyperbox may be something like this. So, the new hyperbox will be this one for one class and will be this one for another class. Okay. So, find that the information which was already gathered for this region this information is lost. Okay. So, as this information is lost, so obviously I am incorporating error while training operation, and as I am incorporating error while training operation, obviously during the testing or classification of the unknown samples, the performance will not be that good. Okay. So, to solve this problem, we had suggested an architecture which is called fuzzy min-max neural network with compensatory neuron. So, that is fuzzy min-max neural network with or in short it is FMCN. So, in case of FMCN, what we have said is, if I have similar kind of overlap, and when I said this sort of containment, it is not necessary that one hyperbox has to be fully contained in another hyperbox. It is also possible that along one dimension it is contained with another hyperbox. So, I can have a situation like this also. Okay. This is also possible. So, containment is only along one dimension, not it is fully contained. So, in case of FMCN, what is suggested is, whenever there is an overlap of this form or whenever there is a containment of this form, do not go for contraction of the hyperboxes to avoid this overlap or avoid this containment. But what you do is, you try to recompute the values within the overlap regions, whether it is over here or whether it is over here. Okay. The logic is, as the hyperbox is created using the information of min point and max point. Okay. So, when you try to recompute this membership value, you try to retain maximum membership value around the min point and max points. As you move away from the min point and max points, you try to reduce the membership value. So, in the graded region, the membership value will actually be a graded membership. At this point, which is the max point of hyperbox belonging to class 1, the membership value of a sample near to this point will be more to hyperbox 1, more to class 1 than towards class 2. Similarly, an unknown point which is near to this max point, this is max point of the hyperbox belonging to class 2. So, if an unknown point is more towards the max point of this hyperbox, its membership value to class 2 will be more than its membership value to class 1. Okay. So, putting this logic, what we have suggested is, we have a graded membership in this overlap region, where the membership value near this mean point will be maximum to class 1 and minimum to class 2, and membership value of an unknown point which is near to this, the max point of class 2 of this hyperbox in class 2, it will have maximum membership to class 2 and minimum membership to class 1. Okay? And in between, the membership value will vary linearly, right. And to do this, similarly over here, if an unknown sample falls within this region, what we do is, we do not disturb the structure of the hyperboxes, the structure remains the same. If an unknown point falls over here, it is within this hyperbox belonging to class 2, though it is also within hyperbox belonging to class 1. but the nearest hyperbox is this one, the red one. So, it will have a membership value 1 to this red hyperbox and the membership value will be 0 to this green hyperbox. Okay. If an unknown point falls over here, it is not within this hyperbox. It will have membership value 1 within this green hyperbox. I am not saying it will have a membership value 0 within the red hyperbox. It will have a membership value to this red hyperbox depending upon its distance from the red hyperbox, but obviously it will be less than 1. Okay. So, by max operator, because this one will have membership value 1 to this green hyperbox, which will obviously be greater than the membership value of this to this red hyperbox. So, by max operator, obviously this will be filtered out and the class membership of this will be given as the class belongingness of this will be given to this green class. Okay. When it falls outside this somewhere over here, again its membership value to this will be more than its membership value to this. So, naturally this will be classified to this class. Similarly, over here, if the hyperbox falls in this region, in the overlapped region or the content region, it will have a membership value of 1 to this red class, membership value of 0 to the green class. Okay. If the point falls somewhere over here, depending upon its distance from these two different classes, its membership value will be computed and it will be put into that class for which the membership value is maximum. So, what we are suggesting is that do not disturb the structure of the hyperboxes, because disturbance of structure of the hyperboxes introduces more amount of error. But retaining the structure of the hyperbox, you try to modify the membership value computation. So, we will have a graded membership within the overlapped region and as well as within the content region, but in the content region it will not be a graded membership value of either 0 or 1, but in the overlapped region it will have a graded membership. So, accordingly, when he suggests this min max neural network with compensatory neuron, okay, this is actually inspired by the reflex action of our human brain. Okay. What is reflex action? The moment you suddenly touch a hot object, or suppose you put your foot on a nail. Okay. Usually, if you have a stimulus, the stimulus information goes to your brain, the brain instructs what to do next. Okay. But in such sudden event, the instruction does not come from the brain. So, you sense the signal, instead of going to the brain, there is a bypass. So, immediately there is a short circuit sort of thing and you get an instruction to your muscle what to do next. So, it is an instant action or a reflex action. Okay. This reflex power that goes on decreasing with your age. As you become older, the reflex action becomes weaker. Okay. So, it is a similar type of concept that whenever you meet such a kind of situation, you take an immediate action. Okay. So, such a kind of concept has been introduced in this FMCN architecture, that if an unknown sample falls within this overlapped region or within the content region, we consider this to be such a kind of sudden situation, right. So, immediately you have to take action without going for much of computation. So, to do this, for every such overlapped region or every such content region, you introduce a new hyperbox or a new node in the hidden layer, which are called compensatory neurons. Okay. So, whenever an unknown sample falls within this type of regions, in the overlapped region or the content region, then only that compensatory neuron will be active and it will try to act as a modifier of the membership computation, fuzzy membership computation of the output layer node over here. So, I will have a set of compensatory neurons. These neurons, these nodes or neurons are actually computing the membership value to a particular class. Whenever a sample falls within the overlapped region or within the content region, then these compensatory neurons will modify these values and the modified value will be taken as membership functions to different classes. So, we will discuss about this FMC and architecture in our next class. Thank you.